Welcome back to Advanced Operating Systems, Week 1, Part 2. Today we'll continue looking at how seL4 is used, how you program to it. Specifically, we start off with looking at the use of capabilities. Last module, I looked at IPC notifications, so the basic communication and synchronization mechanisms, and now we look at how capabilities are manipulated. One of the important things about capabilities is how to derive them. So if you get an object, you have an initial capability to it. There is ways to derive capabilities of the same or lesser strength. One we have already seen, that is badging. That's a form of capability derivation where we use the mint operation to create a less powerful capability because it now is badged and the badge cannot be changed. So we have the mint that takes a capability and a badge and produces this badge capability, and we can also in the same mint operation strip access rights, for example, from a read-write capability, derive a read-only capability. Another way of creating derived capability is granting. So this is the operation of sending a capability over an endpoint to a different protection domain. Inevitably, this is going to create a copy of that capability in the other address space, or actually C space. So the operation of grant produces a copy of the capability, hands it to the receiver, and in order for this to work, the sender needs grant permission on the endpoint, and the receiver, if it wants to receive a writable capability that gives write permission, needs to have the write permission on the endpoint. Otherwise, the write permission will be stripped from the transferred capability. And then there is retyping, which is the basis of all memory management in seL4, which we'll look at later. So the way this works is you have this mint operation, which takes a number of arguments. One is a capability to a C space, represented by a C node. And this is where the space where it operates on. And then you have source and destination capability indices or pointers, which are references inside that C space, then you have the writes and the badge of the new capability. And so what the kernel does, if you do that, it creates at the destination a copy of the source capability with the writes as requested. Obviously, that's an XOR of the existing writes and the ones requested, and the badge imposed on the capability. And obviously, the C node capability required needs to support address space modification. And there is a copy, is a version of that one that takes the C node, a second C node cap for the destination address space, so you can copy capabilities between address spaces. This is an alternative of sending address capabilities via an IPC operation. And the reason it's there is that this is sort of what operating systems will do to set up protection domains for user-level processes, whereas capability transfer via endpoints is a user-level operation. So if you have the write to an object and the write to propagate, then you can use that. As we have seen in seL4, like any capability system, any operation is authorized by a capability, and well, almost any operation. Specifically, this applies to the syscalls. seL4 has 11 of them. One is the exceptional yield because it doesn't require capability. What it does is invokes the scheduler, basically forgoes the present time allocation and invokes the scheduler to do a new scheduling decision. Whether that's a good idea that this is can be invoked without a capability or not, let's leave that aside. There's arguments either way. For now, I'll dodge that question. Then there are the IPC operations we've encountered before, and there are 10 in total, which are constructed from the basic send and receive, which is why I originally said approximately 3, because they're like three fundamental ones. But then there's combinations for various reasons. One is simply efficiency. If you can do a send and receive in a single system call, you save overhead. And typically you do send and followed immediately by receive. So the 2 core operations we already encountered, this is call, which is what the client usually invokes, and reply receive, which is a typical server operation. Both combine a send phase and a receive phase. Then there is send only and non-blocking version of it. So send will block until it can deliver a message. MB send will just try to deliver a message. If there's no receiver ready, it will drop it on the floor. The same with receive. The normal receive blocks until there's a message. The non-blocking variant just fails if there's no message waiting. And there's the non-blocking send receive combination as well, where the send and receive are both non-blocking. And then there's wait and MB wait. So wait blocks until there's a message ready. MB wait just polls whether there's a message and otherwise continues. And then there is the send wait, which does a non-blocking send followed by a blocking wait. As I said, we really should just use call and receive normally. The others are really only for bootstrapping protocols and exception handling. In particular, call is an atomic combination of send and wait, but with the additional semantics of setting up the reply object. So you cannot construct call from a send and wait operation. The atomicity and the setting up of the reply object can only be achieved by call. Whereas reply receive is simply a non-blocking send combined with a receive. Different object types support different subsets of these operations. Endpoints, the normal IPC, support all those. So you can use any of these on an endpoint. Notifications already only support a subset of 3 operations. You can do a signal to a notification. That's an alias for non-blocking send. That's the only way to signal a notification. Doesn't make sense to block on a signal. Similar, there's the normal semaphore-like wait, where you block until the semaphore is signaled. And then there's the non-blocking variant, which is aliased as poll. So the normal way to use it on endpoints would be as through the poll alias rather than the original MB wait. And then any other object types only support the call operation. So the model is, if you invoke a method on an object, this is done by treating the object as a server, a kernel implemented server, and you invoke it with a call operation just as you do a normal server invocation. And each of these kernel objects has a different kernel-defined protocol for communicating with these objects. So typically there is a operation, the method is identified by an opcode, and then there may be more information in the message depending on what kind of object you invoke. This is all specified in detail in the manual, but you don't really need to know much about it because it's basically hidden behind these syscall wrappers. So having got there, let's look at how memory management works. So memory is typed in seL4. You can have, and the types correspond to those kernel objects, and unused memory is called untyped. So it doesn't have a specific type, and pretty much the only operation you can do on an untype is to retype it into something else. So it's basically free template memory, which you then can put to specific use by retyping it into an object type. And one of these types is frames. And frames is a representation of user accessible physical memory. And the main operation you can do on frames is map them into an address space. So this is how you give processes memory to operate, because they need to have mappings in the address space, and you establish those by providing a frame cap and mapping it into an address space. And frames have no kernel defined semantics beyond that. It's typically, it's just something to map into an address space. Everything else is are kernel objects with which corresponds to kernel metadata, and they exist to be able to give the memory to the kernel so it can store its metadata for the operations. And the interesting thing about seL4, which is part of its security story, but it's also what makes life hard for people trying to build systems on top, is that with these mechanisms of retyping or basic object types, seL4 allocates all or delegates all kernel memory management to the user. And the way this is done is by first grabbing as much memory as it needs to boot up, and afterwards never allocating memory on its own. Everything that's left over after boot is handed to the first process, and it then is in total control. So the free memory is given to the initial process as untyped. So it gets set up with a whole bunch of capabilities to untype memory, and then it can do with that what it wants, and thereby implement the whatever system policies that are needed. So the flip side of that one is that whenever you do an operation that requires the kernel to allocate memory for its metadata, you need to explicitly provide that memory to the kernel, and retyping is the process of doing this. This gives you a lot of flexibility. It's a very powerful concept, but it's a huge gun for shooting yourself in the foot. And our experience was that letting students loose on a naked seL4 kernel just meant they all ended up limping along with a single leg or 0 legs. And therefore, we provide a little bit of help by abstracting and hiding a lot of this core memory management into user-level libraries. There are two of these, the CSpace and the UT allocation libraries. And this is how you interface with the kernel until you build up your little operating system. And then dealing directly with seL4 management is sort of advanced level. And the way these operations look like is, well, big lump of code. I'm not going to go into details. It's mostly self-explanatory. And you look up the manual if you don't understand anything. That's way more efficient than we trying to explain it here. As I said, for your project, we give you help in the form of two libraries, the CSpace and the UT library, and you use those for implementing your operating system functionality. So the CSpace library is basically wrappers for system calls that go directly to seL4, whereas the UT library is a pure user-level library, so that allows you to manage capabilities with less than a page granularity. So if you just want a single endpoint, then you have a slab allocator in there that creates an endpoint object that contains many endpoints, because an endpoint is way less than 4K, and then you can, from that, allocate endpoints as you need them, and this is all. The complexity of most of that is hidden in that library. And what you will end up doing in this project is extending this UT library for the needs of your operating system. So now we'll look at how we actually manage address spaces and the whole idea of seL4 memory management. As I said, when the kernel boots up, it grabs memory as much as it needs and then hands all the rest to user level. It's a bit more complicated. There's obviously a protocol for setting up the initial task, the init task. So the protocol says where to fetch the initial user level, the initial. So the protocol specifies where the initial code and data for this init task is found, etc. It's generally part of the kernel image, and then the kernel sets up this task, gets it going. And before it gets it going, it hands it capability to all the free memory. And this init task is then in complete control of the system and can implement arbitrary policies by managing untypes. That's why we often call it the global resource manager, because it is in charge of all the resources. So what it can do is, for example, partition the system and set up a secondary resource manager, or actually multiple of those, and handing them pools of untapped. If you do that, then these secondary systems can totally autonomously operate, and the global resource manager is no longer needed unless you want to repartition the system. So this is one of the nice examples of capabilities. It gives you an easy way of delegation by just handing these untyped capabilities to the secondary tasks. They become totally autonomous. The alternative, of course, which is the more normal way, which you will be using in your simple operating system, is that the init task is the operating system and keeps control of all the untyped, and only hands type memory to secondary tasks. In particular, if it's user level, they generally only get frames mapped into their address spaces, and then they can't really interfere with memory management at all. And all this works recursively, of course. So that's the basic idea. What it is, it gives very strong isolation. If you partition a system that way with no shared resources, then these partitions cannot interfere with each other. There is no way they can communicate. All this is done by retype. So the basic idea is we start off with some untyped memory. So I assume this is, for example, the init task, and it has all the untyped that's left over after the system booted up. And then it can retype that into useful types. So for example, if you have this untyped cap, you can say, retype from that untype 4 frames. And the system will do that, will allocate 4 frames and return read-write capabilities to the caller. And then you've got frames you can play with. And then we can say, okay, now I want C nodes to build protection domains. And so the kernel creates C nodes and capabilities to them and hand them back. And then we can say, okay, we now want threads. So we do retype some of the untyped into TCPs. And now we have thread control blocks, which represent threads. And we can also, as we've seen, derive capability. For example, one of these read-write capabilities, we can mint a read-only one of that one and hand that out for giving read-only access to a shared buffer, for example. And then that, of course, can be revoked. And you can, if you revoke this derived capability, then whoever has it loses complete access to the memory it represents. So that's the basic idea. Okay, now let's look at how we do address spaces. So in seL4, an address space is really a very thin abstraction of page tables, and they look very much like hardware page tables, and they are very architecture specific. Page tables on ARM and x86 are very similar, and therefore the abstractions you see of in seL4 are quite similar. If there was a version for PowerPC, for example, it would look very different. So the ARM and x86 have in common that they have these hierarchical page tables. The 32-bit versions of the architectures have 2-level page tables, and the 64-bit versions have 4 or 5-level page tables. And they are directly represented as corresponding objects in seL4. So we, of course, use an ARM platform in 64-bit mode. So in this case, ARM specifies 4 levels of page tables. At the bottom, a simple page table, then a page directory, then the page upper directory, and the page upper directory, which is called the page global directory, PGD. And the top level page table is what represents an address space in seL4. So a address space reference is really a capability to the top level page directory. And of course, each of these are tables of capability slots. So your page directory is a table that can hold capabilities to page tables. And the page tables themselves will hold capabilities to frames. So that's then the actual mapping from virtual to physical. And if we have another page table which we want to map into this page directory, then we do a page table map operation specifying the page table directory as the destination, and obviously we need to give a specific slot there, and then it will insert this capability in the page directory, and we have now the secondary page table mapped into the page directory. Similarly, if we have a frame capability, then we can say map that into a page table by saying page map, and then this will map it in there, and then we have the new mapping. As I said, the top level page directory is what represents the vSpace, and by creating in this case, the page global directory, you create a vSpace. And deleting it deletes the vSpace. The vSpace is the PGD. Operations that do this are the usual mess of long names and parameters. Again, I'm not going to go into details, except that you see here there's this PGD capability. That's the vSpace reference, and you can map in there then. Interestingly, there's a really bad choice of API here, because it's a mapping of a frame to an address space is an operation performed on the frame as taking the address space as a parameter. It should really be the opposite way. It's going to be very hard to get rid of this. I don't know what the person who did this was thinking at the time. Anyway, it's not a major issue. It's just a an unnice thing, which I prefer we wouldn't have, but we do. So obviously, if you do a mapping, you need a virtual address and a physical address. The virtual address is specified by a position in the page table, and the physical address is specified by a reference to a frame. And the address space, of course, is the reference to the top level page table, and the frame capability is what you map in there. And you need to keep track of this. And there's a bunch of operations that help you doing this. An interesting point is how to set up shared memory. So the point here is a frame capability can only be mapped into a single address space. Of course, a frame can be mapped into multiple address spaces or multiple positions in the same address space. So if you want to set up shared memory, you need to replicate the frame. And this is shown here. So the code shows first the allocation of a frame, and then creating a copy of the original frame capability and mapping that into another address space. So this is how you would share memory, by duplicating the frame capabilities and establishing mappings on the different address spaces. The reason this is done that way is for being able to keep track on where frames are mapped, and that would need extra metadata to represent it, and instead we choose to just have allow a frame cap to be only mapped once. Yeah. And again, there is a whole bunch of other operations that are relevant to all this. When you do your build up your operating system with all its memory management using our UT library, you need to be aware that this library is very simple. It just uses a simple body allocator, and that has some implications. In particular means if you free an object of particular size, then you can afterwards allocate an object of the same size. But if you free two objects of the same size, there's no guarantee that afterwards you can allocate an object of the of twice that size. The body allocator obviously has internal fragmentation issues, and you need to be aware of that. And you need to understand the size of these objects. So here's a table that tells you how big these objects are. Frames are obviously whatever the hardware for base page size is, which is 4K, 4 kilobytes in our system. And then the same applies to page tables. Endpoints are pretty small. They're 16 bytes. Notifications are 32 bytes. So most of the objects are actually fairly small. The only exception is the thread control block, which is 2 kilobytes, which is surprisingly big. That's mostly because the floating point registers use up a lot of space and they need to be stored in the thread control block. These are AH64 values. What you also need to understand is that when you retype untyped memory into a specific object type, the kernel guarantees there's no overlap. So it will not allow you to create overlapping objects. And of course, your libraries won't even try that. However, if you actually try to allocate, to retype overlapping objects by retyping from a frame, from an address in an untype that's already been used, then you will run into very interesting debugging issues. So don't do it. Again, our libraries manage this mostly for you, and but they present a user view which is not necessarily the same as the kernel view, and you really need to make sure that the two stay consistent, because otherwise you will have great fun debugging your operating system. So there's a few other things you should keep in mind. In particular, you need to always have some physical memory up your hip pocket, because otherwise you run into trouble when you need to bootstrap things, where in order to allocate something, you need first memory for capabilities to allocate this, etc. So always keep some free memory around, and you make use of these libraries. They help you. Okay, and the next interesting object type is threads, because they represent execution on the system. So not surprisingly, threads are represented by thread control block objects. That's fairly standard. And the seL4 is no difference here. And thread control blocks have a number of, they describe threads and with a number of attributes. Some of them we have seen, like the vSpace, that's a virtual address space. As I said, this is the page tables. They can obviously be shared between threads, so you have multi-threaded processes. Then we have the C-space, which represents the protection domain, the set of capabilities a process can use. Again, multiple threads can share C-space, multiple even threads from different address spaces can share C-space, in which case these two address spaces have the same protection domain. There's no particular reason why you would want to do that, but it's possible. And then there is a bunch of endpoints, two specifically fault and timeout endpoints, therefore handling of faults. We'll get into details later. Then there's the IPC buffer. This is the thread local storage that is used for virtual registers, which we discussed in the previous module. And then there's the general user registers, the stack pointer, instruction pointer, and the general purpose registers, and scheduling parameters. So there's every thread has a scheduling priority and what's called a maximum control priority, which we won't get into. You don't need that. And a scheduling context, which is the capability that gives you the right to access the CPU. So that represents access to CPU time. We go through a few examples, what you do with them. So when you create a thread, there's a number of things you need to do. You obviously have to obtain, that is either create or reuse, a TCP object. And then there is a configure call that allows you to configure these thread attributes, so associating C-space, vSpace, endpoints, etc. And then you need to set scheduling parameters, and in order to make the thread runnable, give it a stack pointer and an instruction pointer, and may possibly provide other register values. And this is done by the write registers interface. After going through that, your thread is initialized and in principle can run. If the write registers system call was given the resume target value flag, then the thread is immediately runnable. Otherwise, it is still blocked and needs to be made runnable but with a resume library call. This is summarized in this piece of code here, which shows how you create a new thread in your own address space. So this reuses the caller's address space and C space. So we allocate a frame for the IPC buffer, allocate a slot in there, and then just fairly obvious system calls. And as I said, you'll need to look closer in how these operate. If you do use multiple threads in the same address space, which you want to do for your operating system, then it's a good idea to wrap all this in the library. A few things to keep in mind. Stacks are completely user managed. The kernel doesn't care about stacks. All you know is there's a stack pointer, and you need to make sure that there is actual usable memory for the stack pointer to point to. And all the kernel does is context switch those things, like the normal user general purpose registers. So the stack itself must be allocated and managed by userland, and of course you typically hide that in a library, but you need to understand that if you have multiple threads, for example, in the same address space, then there's a certain amount reserved for every stack, and if it grows beyond that, it grows into some other data structures in possibly another stack. So you need to be careful about stack overflow, because that can be a pain to debug. And the spatial danger is here automatic array. So assume you have two threads in the same address space with their stacks allocated somewhere, probably not too far apart. And then you do a function call that allocates a big automatic array. That's, of course, a silly thing to do. Some people do it, and you might be tempted, if you don't think about things too carefully, to actually do that. And the inevitable effect is going to be this is going to overrun your stack, your allocated stack frame, and run and override other data structures. If you do that, you'll have fun debugging, because you get really funny effects where suddenly variables that don't belong to the thread suddenly change magically. If you have something like that, look exactly what you're doing with stacks. You might have a stack overflow problem. Okay, to create a new process, you need to create a thread in a new address space, and typically a new C space. And again, this is sample code that shows you how to do that. And in particular, it has the invocation for configuring the TCP with the IPC buffer, etc. So have a good look and how to do that, and compare it with the existing code to understand how to do this. Important for threads, of course, is scheduling, and so you need to understand how scheduling works in seL4. seL4 has a hard priority scheduler, which basically means there is a fixed number of priorities, 256, and they are strictly observed by the kernel, in the sense that the kernel scheduler will always pick the highest priority runnable thread, and if there's multiple of these runnable threads at the same priority, it's round robin within that priority level. And in particular, the kernel will never change that priority, so that's they're hard in that sense. This is very unlike a system like Linux or Windows, where your kernel will mess with priorities, adjust them up and down all the time, etc. seL4 doesn't do that, because that's policy. You need to implement that at user level. The other important thing is, in order to run, a thread needs to have a scheduling context. As I said, this is the capability that gives you access to the CPU time. If you don't have that, you can't consume CPU time. And the scheduling context contains two important things. It contains a few other ones, but these are the most important ones to understand. It has a budget, and the budget starts being consumed when the thread is scheduled and executing. And if the budget is exhausted, so the thread gets to the end of its budget, it is no longer runnable, and it will be removed to the run queue. When does it get back? This is specified by the period. So the period tells you how often you can get a new budget. And if you're at the end of your budget, you get suspended until the next period is up, you get a new budget, and then you're runnable again. If the two are the same, which in your case will usually be the same, the case, then the budget operates like just a normal time slice. When you get to the end of it, you get put at the back of the run queue at that priority level, and you get, whenever the schedule gets to you again, you get running. The reason why we have this particular setup is, on the one side, because it minimizes policy in the kernel, but on the other side is the goal is really to have a system that is suitable for hard real time. Anything else, any sort of best effort policies you can layer on top by basically having your operating system adjust scheduling priorities explicitly. So you can raise and lower priorities of the threads you're scheduling and could implement for example, a fair scheduler. But that's manual work. Okay, so much about threads and scheduling. Now let's look at the last mechanism we need to understand, and this is how interrupt and exception handling works in seL4. Let's look at exception handling first. There is a total of 5 different exception types defined in seL4. Invalid syscall. Sometimes this represents a bug, basically an instruction that doesn't exist, but it can be used for instruction emulation. For example, if you have a processor that doesn't have an FPU, a floating point unit, then you can still execute floating point instructions by causing a trap and let the exception handler emulate the floating point instruction. So this is how a soft floating point works. And the same approach is used for virtualization. So invalid syscalls can actually be useful, but they can also represent just invalid code. Then there's capability faults. They happen if a capability is presented to the kernel looks it up in the C space and either doesn't find a capability, or the capability it finds there does not authorize the attempted operation. And then there are page faults. And again, page faults can arise for various reasons. Either you access a address that is not mapped, and that can be benign or not. It can mean there is a memory fault, a seg fault equivalent, or it can just simply mean you have to grow your stack and heap. And of course, this is the job of your operating system. So if your user code starts off with a single stack frame, and it may need more than a single frame for its stack, you need to grow it dynamically. Or same with a heap, you allocate an initial heap, and then you need the equivalent of set bulk to grow the heap if the process needs more heap. And you may even have to load dynamic libraries, etc. And then there's architecture-defined exceptions. There are things like divide by 0, unaligned excesses, etc. And as it says, they're dependent on the architecture and are specified in the ISA of the relevant architecture. And then there's a timeout, and this is one that gets raised when you reach the end of your budget. That triggers a timeout exception. The way seL4 handles these exceptions is that it sends a message to the fault endpoint. And for the top 4 exceptions here, this is the exception endpoint. The timeout is different. It has its own endpoint. So if a timeout occurs, then an exception message is sent to the timeout endpoint, not the exception endpoint. It's actually optional to have that. So a thread does not have to have a timeout endpoint, in which case the timeout is just simply silently ignored and the thread is suspended or put at the end of its scheduling queue. For your purposes, you typically don't need timeout exceptions. You can just ignore them, let everything run with a budget that's equal to the period, and then you don't need to worry about these at all. Okay, so this is exceptions. And then there are interrupts. And they use their own two special objects. It's really one variance of one type. There is a IRQ control object, and there's only one of these in the system. The whole point of this IRQ control object is to create IRQ handlers. So this is really one of the things to control the system, and your operating system will not let that get away at all. And so you can use this IRQ control to create IRQ handlers, and an IRQ handler is the right to basically deal with interrupts. So we can create one of those per interrupt source. And they are used for associating and disassociating handlers with interrupt and do interrupt acknowledgement. So what the IRQ handler allows you to bind a driver to an interrupt notification object. All interrupts are represented as notifications in seL4. So you have an interrupt source, which corresponds to an IRQ handler, and you can bind that to a notification, and then whoever has the right to read from this notification basically is the interrupt handler. So your handler will then perform a wait operation on this notification. When the interrupt gets in, the kernel signals the notification. The interrupt handler does its job handling that, and eventually gets back to acknowledge the interrupt, to tell the kernel to re-enable it and be able to ready to receive the next one. And here we have a little piece of code. Oops. And here's the code that shows you how to do that. And a device driver is obviously an interrupt handler. So in seL4, that's all done at user level, like any other L4 kernel. And so it needs to handle interrupts, as we just described, and then communicate with the rest of the operating system. So this is typically done by an IPC protocol using invocations of functions in the OS, or the OS more likely invoking the handler, and it accesses device registers. ARM uses memory mapped I/O, so these are just normal mappings. You need to understand the magical physical address of where these registers live and map it into the address space of the driver, and then the driver can control the device. So this is an example of how this is done. So this is a map call that uses the magic physical address of the device to map it into the driver address space. All right, and this is all the basics you need. You are doing your project on this Odroid C2 platform, which is a quad-core ARM A53 processor. It has a whole bunch of devices. Most of them are totally irrelevant for you. The ones you need to worry about is the serial port, which is used for debugging, and a timer, which is used by the kernel for enforcing budgets. The kernel has drivers for those two. The serial driver, it only has if it's compiled for debugging, and a timer driver it obviously needs. All the other drivers are completely at user level, and there is nothing in the kernel for dealing with them. And one of the devices you need to worry about it is the Ethernet, because you will you use that for communicating with the network file system, which you use as a storage device for implementing for implementing demand paging, as well as loading ELF images for run on the system. And we have a serial driver for, we expose a serial interface over this Ethernet, which you will use in your initial startup milestone for playing with a simple driver interface. Okay, and I'll leave you with a little video clip, which is from the DARPA HACMS program, which shows a helicopter. It's a Boeing helicopter. You can see here, if you look carefully, there's the yoke, but the pilot doesn't touch it. This helicopter is flying autonomously. And of course, the cool thing is it's flying on seL4. So this shows you that you're working with an operating system that is totally real-world capable. And this is on a flight that was done 2 or 3 years ago in Arizona at the Boeing facility.